Take a look at these four series of numbers and tell me what is the relationship between each series and between the numbers in each series. It's kind of a rhetorical question. It's really, really hard to look at data in this format and get any useful information out of it. However, if we plot these as a simple scatter diagram, then the relationship jumps out really quickly. You can see there's a very strong correlation between X and Y in each series. Some series have a stronger correlation than others. Some series have some outliers. You notice 3 and 4, there's a couple of outliers there, which might represent bad pieces of data. It might represent a reason for us to modify the model that we would have if we didn't have it. The point is that it's possible to glean a lot more information a lot more quickly, very often, when we look at data this way, in terms of pictures, graphs, charts, and maps, than it is to look at the raw data itself. And that becomes more true the more data we have. Now, this process of turning numerical data into pictures is called data visualization. And I'm a software developer. I've been doing that for a long time. That's a big part of my job, is turning numbers into pictures. I was a consultant for over 20 years. And we'd collect data and we'd show it back to the user in some usable format, often as a graph or a chart or a map. A lot of us do that. How many software developers in the house? Almost everybody is. And when we do this, we use tools. This is not a tools talk, but there's a lot of really good tools out there. You know, they've evolved to the point where they're ridiculously easy to use. You point at a data source, you select a type of a chart, and then next, finish, and bang, you have a pie chart. But what if the pie chart is not the best way to display your data? Or a more fundamental question is, what do I even mean when I say best way to display data? And this is something that I really didn't think about for a long time, for a good part of my career. I would hit next, finish, and problem solve. I'm on to the next problem. And my purpose today is to get you to maybe stop for a second after you hit next, finish, and think about some of the principles that we're talking about. How can I make my visualizations a little bit better? Not so much in terms of choosing the right tools. The tools you're using are probably really good. I mean, Excel is a really cheap tool, and it does a great job. And there's, every control vendor has a set of visualizations. They're really good. They're easy to use. This is not a tools talk. I want to talk about some principles of data visualization. Because my guess is that maybe, like me, a lot of you are not thinking about that. Now, one person who is thinking about it is Edward Tufte. Edward Tufte is a professor at Yale University, and he's a leader in the field of data visualization. He writes about it extensively. He has done so for decades. A lot of what I'm going to present today came out of his writings. This is an excellent book here, The Visual Display of Quantitative Information. He self-published it about 30 years ago, and it's still very relevant today. When he began his study decades ago about data visualizations, he began looking at pictures of data that spoke to him and trying to find out why they spoke to him. Why were they good visualizations? And they weren't necessarily computer generated. This one, for example, is a train schedule from the 19th century in France, and it shows this along the y-axis are the stations in France where the trains stop, and along the x-axis are the times of day. It goes from 6 a.m. 24 hours later to 6 a.m. the next day. And these vertical lines, these diagonal line segments represent the routes that each train takes. So the left end point of each line segment is the time and place of a departure of a train, and the right end point is the time and place of a destination. So it becomes a simple matter of following one of these lines to see that there is a train that leaves Paris at about 12:20 in the afternoon, and it arrives in Tonnerre at looks like about 6:30 in the evening. Once you know, it's not a perfect visualization, but it's simple. It's easy to read, and it's maybe even easier than airline schedules. They could learn a thing from its simplicity. Here's another one. This shows each vertical line is a decade, and there are several graphs plotted along the same x-axis. X-axis is time here. The bar chart in the middle is the cost of a bushel of wheat in England for each decade, whereas the red line below it is the wages paid to a mechanic over that same period of time. So what we're seeing is the cost of commodities and the cost of labor. And you can see that they more or less follow, they go up and down at about the same rate, except that the cost of commodities is a lot more volatile than the cost of labor, which might be related to the lines at the very top up here, which show the monarchs that were reigning over the United Kingdom during those periods of time, or more likely the wars that those monarchs were waging. So we can start seeing correlations here between this data, and we can start coming up with hypotheses as to why those correlations exist. And we do so because they're all sharing a common axis. In this case, it's time is the x-axis. Here, of course, is geographical data. This is from the 1960 United States Census. I know it's really hard to tell, but I'm actually from the United States. And this shows every county in the U.S. There's, I think, about 2,000 counties in the U.S. There's a lot of them. This is a lot, even in aggregate. This is a heck of a lot of data. But what it shows is concentrations of high-income families in each county and concentrations of low-income families in each county. The darker shades represent high concentrations. Lighter shades represent low concentrations. So on the top, that's our poor families, low-income families. Dark red means lots of poor families, those counties. Light red means very few. And on the bottom, these are high-income families. So there's a lot of rich people in Southern California, on the southwest part of the U.S., very few rich people in the southeastern part of the U.S. They almost correspond with each other, but not entirely. There are counties in Alaska, for example, that have a high percentage of high-income families and a high percentage of low-income families. There appears to be no middle class, at least in 1960, very low middle class at that time. And in fact, where I come from, where I recently moved from Detroit to Chicago, two big Midwestern cities. Well, Detroit is not doing very well financially, but I can look at this map and I can see that it seemed to be doing pretty darn well in 1960. It seems it's fallen on hard times over the last 50 years. This map would probably look very different if it were drawn today. The point of this is that there is a lot of data that we can just take in very quickly, that human beings have the ability to look at. I mean, this is millions of pieces of data, but even in aggregate, it's thousands of pieces of data. And because we're using shades, our eyes can really quickly pick light shades, dark shades, in a way that if they had chosen, the designers of this graphic had chosen to use, like, let's say, blue for low concentration and orange for high concentration, probably not so much. But shades, light and dark, even if we're colorblind, we could see that. Then there's this graphic. This is Edward Tufte calls this the greatest data visualization ever created. It's created by a French engineer named Charles Menard, and it's actually a map of Russia, and it shows the advance on and retreat from Moscow by the Emperor Napoleon near the end of the Napoleonic Wars. It has a couple of lines here. This tan line at the top right here represents the route that Napoleon and his men took as they marched eastward toward Moscow. So here is the Polish-Russian border right here. Over here on the far right side is the city of Moscow. This is the route as they marched eastward. A few troops branched out here, and then this black line below is their retreat, their march away from Moscow back into Poland and towards the rest of Europe. The thickness of each line is proportional to the number of troops that Napoleon had at each point. Now, knowing just that, you can look at this picture and you can see that this was a disaster for Napoleon. Napoleon entered Russia with almost 500,000 men, and his expectation was that he would overwhelm his enemy with superior numbers and live off the land. That's what he had done by conquering the rest of Europe prior to this. But that didn't work out that way. Does anybody know what happened? Any Russians in the audience? Tell me what happened. Winter is a factor. So, are you Russian? Yeah. Good man. So the Russians, they were badly outnumbered. So rather than engaging him directly in battle, they retreated. And as they retreated, they destroyed their farms and their towns and their livestock. And they stretched Napoleon's supply lines so thin that he really didn't lose that many men to Russian bullets, but he lost a huge number of men to disease and starvation and suicide and desertion. And You can see that. You can clearly see this. By the time he reached Moscow, that 500,000 men was barely 100,000 men. And when they left about a month later, the trip back was even worse, because the trip back is when the bad winter started. And we can see that down here. There's an extra line down here showing the temperature on the dates during the way back. I know the numbers are very hard to read, but down here on November 26th, it reached a minus 40 degrees, which might be Fahrenheit, it might be Celsius, but it doesn't matter. It was minus 40 degrees. And this 100,000 men they left with, even with reinforcements arriving, was down to 10,000 men. 90% attrition. These numbers just jump out at you when you know what these things do. There's a huge amount of information packed into this small amount of ink being used. I think you can see why Tufte loved this visualization. On a single axis, Charles Menard has managed to plot number of troops, position of troops, direction of movement, time, and temperature. Lots of information, and we can make comparisons and come up with hypotheses as to why correlations exist between all this data. Okay, that's some good stuff. Let's talk about some of the bad things that you can do with visualizations. And in mind of Edward Tufte, the worst thing you can do with your data visualizations is to lie to your viewers. Now, in the United States, where I'm from, we have adopted an Australian named Rupert Murdoch. And he has a TV station called Fox News. And sometimes they stretch the truth. Here's an example of it. This is, we're having a presidential election in the U.S. right now. You probably don't read about it at all, but it's a big deal to us. And this is actually from the last presidential election. President Obama was running for a second term, and so Fox News put this graphic up to plot out unemployment rate during that time. There's a few problems with this. One is that the zero axis is not on there, so fluctuations look very large. But the real big problem here, the reason I say this is blatantly wrong, is this number, 8.6. The very last number is actually plotted at the same level as 9.0 and plotted above 8.8. 8.6 is actually the lowest number on this graph, and yet it's plotted as one of the highest numbers visually. It's hard to imagine that they weren't trying to mislead people by hiding the fact that the unemployment had dropped at the very end of this graph in context, because they did not endorse Obama during that election. Here's another one here. This is from a mining company. I don't think this mining company exists anymore, but this was an annual report of a mining company showing net income over the course of 5 years. It's not at all obvious when I look at this that this number right here is a negative number. This company actually lost money during one of those years. And the reason it's not obvious at all is because they've chosen to show that negative $11,000 as a really tall vertical line, and they've also chosen to omit the zero from this graph. Again, I think this is deliberate. But the problem is that when I notice something like this, it causes me to call into question every number and every visualization, every chart in this graphic, which is probably the opposite effect they were hoping to achieve by doing this. Here's another one. This is from the New York Times. And this one actually I don't think is deliberate, but it's still wrong. It's still misleading, very misleading. This is from I need a little more backstory. I'm going to give you a lot of history here. Is that okay? So this is in the 1970s and 1980s, we had an energy crisis. We suddenly decided, at least in the United States, that we were very dependent on foreign fuel consumption, and we better stop driving these gigantic cars. That's what we did. We drove big, long cars with the Corinthian leather, and they got horrible gas mileage. And so the United States government stepped in and said, car companies, you must build and sell more fuel-efficient cars. So what we're going to do is we're going to take the fuel economy of every car you sell, add them all up and divide by the number of cars, and that number had better be X. And if it's not X, if it's above X, then there'll be penalties. That's pretty harsh. They had never done that before. That was the bad news for car companies. The good news was they had some time to adjust, and that's what this is showing here. It said that in 1978, that number, the average miles per gallon of every car sold, had to be 18 miles per gallon. It would go up a little bit every year, 19 and 20 and 22, et cetera, until it reached 27.5 and 85. So this graph, as the lines get bigger and these numbers get bigger, totally makes sense. Except that if you look at this line right here representing 18 and this line representing 27.5, they're not at all proportional. 27.5, yes, it's bigger than 18, but it's not as much bigger as this line suggests than this is. So it's misleading. You could argue that this picture does show the direction of change. So what if it's the magnitude is off by a little bit? But is it off by a little bit? I mean, how much is it off by? That's a question that we start to ask ourselves. This is something that Edward Tufte actually came up with a measurement for. It was my favorite name of any ratio in all of statistics. He came up with a way to measure this. He called it the lie factor. And the lie factor is simply the size of the effect shown in the graphic divided by the size of the effect in the data that graphic is supposed to represent. Ideally, it should be 1. Now, this is a hand-drawn graph, so if it's off, if it's not quite 1, that's totally forgivable. But it should be close to 1 at least. And in this particular graphic, the data increased by 53%, quite a bit amount, from 18 to 27.5. But those lines increased by 783%. So this thing is lying to us almost 15 times over. It's not off. The magnitude is not off by a little bit. It's off by a lot, which is a problem. It's a lie. But I said originally I didn't think this was deliberate. I'm curious. I could be wrong. I don't know the people that created this at the New York Times. But does anybody have any theories why something would be that wrong, other than they totally wanted to mislead their audience? Yeah. For the graphical effect. That's my theory as well. So you said they went for the graphical effect, and I think that's right. I think what happened is that the person that created this graphic was not the automotive correspondent. He was not a statistician. He was not an engineer. He was an artist. The responsibility for creating this picture was moved away from the people who understood the data, the automotive reporting department, into the art department, because the New York Times decided that it was more important for this to be pretty than for it to be right, which is dangerous in my opinion. It's because it's a lie, and it's a lie even if it's unconscious. Even if they didn't mean to do it, it's still wrong. It's misleading us. Here's what the truth looks like. It's yeah, it went up, but not nearly at the rate that picture showed. All right, here's another one that's wrong for a different reason. This is showing the decreasing number of family practitioners in the U.S. or in California for from 1964 to 1990. This axis isn't proportional, but I don't think that's the big problem here. The big problem here is that they're representing this number 27%, 16%, and 12% by these shrinking doctors. The big problem with this picture is that they've chosen to represent a one-dimensional data point as a two-dimensional object, and that object is actually varying by both its height and its width. So as you learned in elementary school, the size of an object is proportional to both its height and its width. So if they both change, then the size will change with both of them. So even though the height of this doctor is about twice the size of the height of that doctor, he's about 4 times the size in area as that doctor is. So just simply because they've chosen to represent one-dimensional data points as two-dimensional objects, this is a lie factor of almost 4. And if we take this, here's another example. I think this is from Time magazine. This is here they've actually tried to draw a 3-dimensional picture to represent the price of oil during each year. And if we take the metaphor that they're presenting to us, then 3-dimensional objects, of course, the size of them is proportional to their height and their width and their depth. And so these barrels of oil are increasing extremely, an order of magnitude taller than you would expect. As far as I know, this is a record lie factor. And I don't think it was deliberate. I think they thought 3-dimensional. Let's make it pretty. And this is the way it came out. This is the cost of focusing on aesthetics over accuracy. Here's one. This is from the London Times. This is actually much more accurate here. This one also I like because it uses both real and nominal dollar values, which was a big deal. The time period presented here was a period of high inflation. So there was a big difference between the real dollars are dollars that are adjusted for inflation. Anytime you have money over an extended period of time, you should always adjust it for inflation, period. Here's another one. This is a graphic showing the commissions paid to travel agents for 4 different airlines for 3 different time periods. And for each of these 4 airlines, you can see that they went up from period 1 to 2 it went up, and from period 2 to 3 went down. That happened for all 4 of these airlines. What's not at all obvious here is that this third period is a 6-month period. The other 2 are 12-month periods. Of course, it went down. It was only half as long. It's not obvious at all whether it went down proportionately. It's really what they should have done is either annualize that third period or split these other 2 up into 6 months. As it stands now, it's pretty much useless, that third period. So it went down. So what? Let's see. Context. Context is really important here. Here's an example. This is the number of traffic deaths in the state of Connecticut. Connecticut's a state in the United States, and there's 2 points here: 1955 and 1956. I'll call out that I've actually omitted the 0 axis here. I'm not trying to emphasize the slope of the line, just simply the fact that they went down. But they reduced from 325 to about 270, or maybe at 280, I guess, during that year. And the reason those 2 dates were chosen is because that's when Connecticut started to strictly enforce speed limits. Prior to that time, I think they had speed limits, but they weren't strictly enforced. And it looks like enforcing speed limits saves lives. It kind of makes sense, but does it? We don't really know. We can't infer that from this graphic because there's really no context. We don't know what happened before 1955 or after 1956. This graphic could look like this or this or this. We're only looking at 2 points, and in fact, we would draw different conclusions depending upon what the graphic looked like. In fact, the full data looks like this. It was trending upward prior to 1955, and after 1956, it went down and it continued to go down. So this is actually, with this context here added, this is pretty strong evidence that forcing people to drive slower will save lives. And here's even more context. These are the states that are contiguous to Connecticut, and these are the deaths per 100,000 because many of these states have a lot more people than Connecticut. And you can see in these other states, the number of deaths after 1956 either remained level or went up. Connecticut is the only one that was significantly reduced number of traffic deaths. So the context here provides a lot more information than just a couple of points. All right, I'm going to pause here and just reiterate some of the things I talked about so far. If you're working with data, keep your data proportional. Don't keep your lie factor to 1. Don't lie with your data. And you do so by keeping your data representation proportional to your data. And one way to avoid that is with the don't use 2-dimensional or 3-dimensional data or visualizations to represent 1-dimensional data. I should point out that bar charts, those are 2-dimensional objects. They don't have that problem because the width of a bar does not change. It's only when the width and the height change, they both change, that we have this problem. Adjust for inflation over any extended period of time and provide context. Pause here for questions. Any questions so far? All right. Data ink. This is a concept that goes back to when we used to print. You guys probably don't remember this, but we used to print stuff on paper. We'd write a chart out, and we'd all have these inkjet printers at home and laser printers at work, and we'd print it all out. Well, we don't do that anymore. We look at stuff on screen usually, but we still think conceptually the dark parts are the ink. And there's something called the data ink ratio. This is another invention of Tufte's. The data ink divided by the total ink is the data ink ratio. And the data ink is the part of the ink, the dark parts, that directly represent data. So the most this can ever be is 1. If all the ink is data ink. Your goal should be to maximize this ratio within reason. And I'm going to talk about what that means, within reason. But you may be asking yourself, well, all right, well, if the data ink is the part of the chart that directly represents data, what else is there? What else is, there's other ink on the page. What could there be? And so let's talk about that. For one thing, there could be redundant data. If you've got the same data represented multiple times, then only one of those is data ink. The rest of it is kind of wasted. It's a distraction. So here's an example here. This is a bar chart. So bar charts aren't perfect. They're not really efficient. And this is just 1 point. It represents the number 35.9. And let's count the number of ways that it represents, the way this visualization represents 35.9. First, we have a vertical line here that's 35.9 units tall. Another one over here, also 35.9 units tall. This bar right here at the top is 35.9 units from the x-axis. The shaded area is 35.9 units tall. The number is 35.9 units from the x-axis, and it is, of course, the number is, in fact, the number 35.9. There's a lot of redundant information in this. So it has a very low data ink ratio. And I won't go through that same exercise here, but a lot of people fall in love with 3D graphs. Well, 3D graphs, there's a lot of ink here. There's a lot for the mind to absorb just to get that one number. And so the idea of keeping the data ink ratio high is to remove distractions and focus on the data as much as you can. And this is not a good way to do it. The 3D graphics tend to be very bad at that. So that's redundant data. Metadata sometimes is important, but it isn't data. It is ink that is about the data. It maybe tells part of the story about the data. So here's an example here. It doesn't really matter what we're plotting here, but it's a scatter diagram with a trend line through it on some graph paper. And what's the data here? Who can tell me what the data is? The data ink. The dots. The dots are the data ink. Everything else is metadata. I mean, it could be important, but it's not data. Only the dots are the data. What happens if we remove some of this? Like, for example, what if we remove some of the grid lines? I'm going to show that to you again. There's before, there's after. This, I think, is way better. I don't have the distraction of all those grid lines. The data jumps out at me. I've also, I don't know if you can tell on the screen, but those lines, they used to be black, and now they're light gray. And this is a lesson that if anybody remembers using like the very first spreadsheets for Windows, Lotus and Excel and Quattro Pro, they have borders between the cells, and those borders in the first version were black. But now they're not. Now they're gray because the people that created those spreadsheets realized those borders are not the data. The numbers are the data. The borders are metadata. De-emphasize the metadata that makes the data jump out more. In fact, maybe we don't even need those. We could get rid of them. The data jumps out even more. Maybe we don't need the top and the right border. Maybe we don't need all the numbers along the left side and along the bottom. Maybe fewer numbers. Less ink means the data jumps out more. Let's take it a step further. What if we remove the trend line? That's metadata. That's not data. I can see the data better, but in this example, I think the trend line adds something to it. I think it emphasizes this a linear relationship. I'm going to put it back. So without the trend line, my data ink ratio goes up, but I'm going to put it back even though it lowers my data ink ratio because I want that information. And that's why I talk about, this is an iterative process. I talk about let's increase that ratio within reason. Here's another one. This is actually by Linus Pauling. Linus Pauling is I'm a great admirer of his. He has a Nobel Prize in physics and peace. The only person to have both those Nobel Prizes. Just an amazing man. And he got it. Check it out. No grid lines. He replaced them with these little plus signs instead. This is the atomic volume versus the atomic number for dozens of elements in the periodic table. But did he really need those plus signs? Get rid of them. Why not? And get rid of some of the lines on the axis. I think this is better. Now in this case, he's drawn some lines here. These lines are actually the rows in the periodic table that represent the number of shells of electron. If I remove those, we lose a lot of information. I would definitely put those back in. That provides a lot of information. And then he's even labeled, or whoever did this adjustment here, has labeled the first element and the first atomic number in each row. So each one of these has common characteristics. And so it's important to group them together. So maybe we could learn, maybe Linus Pauling could learn something from us. I actually have a degree in biochemistry. That's what, nobody knows that about me except for you guys. So, and people that are watching the video there. Here's another. So we saw this before. This was the train schedule, and it has. You probably now see a lot of problems with this train schedule. But one thing that isn't obvious is there's a problem with it. What if a train is in transit at midnight? If that happens, now our eyes have to move over here to find out the exact schedule, which is hard. You should never have force users to move their eyes over multiple parts of a graphic. We can solve that problem by significantly reducing the data-ink ratio. So I told you we should, we should increase the data-ink ratio, but in this case, if we reduce it by copying half the graph over to the right, that solves that problem. Now you're probably thinking, well, we could probably offset that by removing some of these grid lines, which is true. So there's a way of helping that as well. All right, some principles about the section we just talked about. Think about the data and what is the data here, what is the data ink, and show the data, show the data, show the data. This part of Tufte's writing is what changed my work more than anything else. When I was a consultant, I had a lot of people that would come to me and say, hey, we've got this application, we built our whole business on this Excel spreadsheet. And we need to, but it's good. It's growing too big for Excel, so we want you to write it in, ASP.NET, SQL Server, or whatever it is. And but we want you to make it look just like Excel, because our people are used to Excel. We don't have to retrain them. And so they would have these mock-ups with all these grid lines all over it and all this extra ink. And I said, what if we got rid of all these grid lines? I said, oh, we can't get rid of those. Our people, they'll freak out. They're used to them. What if we made them gray and got rid of like every other one? And we'd have that conversation. It really changed the way I was doing it, not just in terms of creating charts and graphs, but changes in terms of changing the user interface, because all these things are just distractions. This metadata, this redundant data. All right, so think about the data and think about the data ink and the data ink ratio. What's not data? Get rid of non-data, get rid of redundant ink, get rid of metadata. But every time you do that, this is an iterative process. Take a step back. Take a step back and say, is it better? If it's not better, put it back. But chances are it is better. Chances are you have a lot of extra ink in your visualization after you've hit next, finish. All right. Vibrations, what are we doing for time? We're until 6:40. Okay, we're good. Vibrations are less of a problem now than they were back when we were printing out with laser printers. We'd have stuff like this, black and white laser printers. We'd use things like this, and people would look at it. They'd have seizures and stuff like that because there's a very real effect. It's called the moire effect. And if you stare at this thing, it looks like it's moving, and epileptic people actually literally there would be problems for them. Even if you're not, when you come up with crap like this, it's just impossible to read. Let me see. Here's an example here. So I look at this one here. I really hate the fact that this has a legend. This is another example. I have to look up and look down again and see where everything is. So if I look at like the bottom part of it here, I see, those are diagonal lines. Those are unfinished oils? No, unfinished oils are diagonal lines going this way. Those must be the crude oil. I don't know. Let's see this. Here's another example here. Same sort of thing. This was the number of news stories printed during the 1972 presidential election. And I've got to figure out inflation. What kind of diagonal line is inflation versus unemployment and so on. It's really hard to read. Some of these things, they're diagonal lines that are close together or maybe a micron further apart. Don't do that. This is much better. Colors are better to represent, assuming that your users aren't colorblind. If you know your audience, you want to think about that. But really, labeling directly is the best way to do this. If you can label your things directly, that's way better than a legend. And then even better than this, actually one of my audience members, I gave this talk about a year ago, and somebody said, well, why don't you just sort those? And that way you can tell, like competence and inflation, I'll go back to the other one. It was hard to tell which one was higher, but you sort them. If you think about what kind of natural questions would people ask, in this case, it's pretty obvious that y-axis, the percent of articles, is the number they want. About sort by that number and be able to very quickly see which is the highest one, which is the most important one. Chart junk and ducks, those are the same thing. This is stuff that it's not even metadata. It's just decorations that people throw on just to make things pretty. It was named after, Tufte named it this ducks after this building in Flanders, New York that is shaped like a duck for no other reason than that people will be driving down the road and say, oh, look, there's a building. It's shaped like a duck. Let's go check it out. It's just to call attention to itself. There's nothing about the duck shape that makes it better as a building. And anything about your graphics that doesn't make it better as a graphic, you should throw away. This one right here, somebody tried to get clever. I think they were making the curved lines to emphasize the downward slope of this graph. But now I don't even know whether I should be looking at the left point of it or the right point of it. Stuff like this. Here they're using colors instead of shades to represent the values, the high and low values. Same thing here. They're impossible to read. And this is a real graphic. This is from an educational journal. There's only 5 points of data in here. I always have to look at this. It is for 5 different years, it is the percent of students in college who are under 25 and over 25. So I guess there's 10 points of data, but if you add them up, they're 1. So if you had 5 of them, you could just subtract 1 and you get the other 5. And they've chosen to show these points of data with just 5 different colors and these curves. I'm convinced these curves mean absolutely nothing. The 3-dimensional aspect of it means nothing at all. And then even the fact that these numbers, I know this to be true, and I still have trouble grasping it, that this, for a given year, this number plus this number always equals 100%. This number plus this number, they always equal 100%. I know this to be true. I still don't see it in the graph. It doesn't jump out at me. It's just really, really hard to read this graph. And I was looking at this graph. It came out of this educational journal that in Tufte's book he quoted it. And I always wondered if the guy that created that graphic was in a bookstore one day and came across his own picture in there, and for a second before he read the text thought it was very flattering, but it's not. I started thinking, what's a better way to depict the same data here? And I came up with, I think, the best way to depict this data is just like that. This is actually really simple data. Small data sets you might not need any kind of visualization. Let me get another column here that's percent of students over 25, and there'll just be 100 minus that. But still, these are, you don't necessarily need visualizations. All right. A couple other things here. Multifunctioning graphical elements. These were important. This isn't always possible in whatever tools you have, but I thought they were really clever, so I'm going to throw a few of them out here. These are the number of troops that were deployed during World War I. A clever desk sergeant with a typewriter created this graphic, and it is not only the data points themselves actually are the divisions that were deployed to France during that time. So you can actually look at the data and not only see them going up, but you can see which data which divisions were being deployed. So the data ink ratio is very high in this one. Same thing here. There's no rule that says that you have to have everything projected down onto the x-axis. There's no rule that says you have to have lines on the x and y axis. In this case, rather than having points here projected onto the axis, the points themselves are the data. And there's also no rule that says you have to have equidistant values on each axis. So in this case, we actually have the data. You don't have to do any interpolation. That data is actually here on this. Data density is a concept here. Again, this is something that there's a formula for it, but I think it's meaningless when we talk about seeing things on screen because we don't really know the area of the graphic. But the point about data density is that you should not be afraid to have high data density in your graphics. If you're practicing good practices about data visualization, human beings can take in a lot of data. So this is obviously a very low data density graphic. There's only a few pieces of information on there. This is a high density. It's got weather information for every single day in New York City. It's got the high and low temperature. It's got information for precipitation for the year and the actual this year versus the normal every single month. It's got the relative humidity every single day. There's tons of information in here, and you can see, well, look, it's hotter in the summertime and cooler in the wintertime. We can, as human beings, zoom in and get a lot of information and zoom out and see it very quickly. We can process a lot of information if it's presented really well. This is even more information. This is sunlight data. So cloudy days are represented by it's backwards in my opinion. It should be the dark part should be the sunlight, whereas the light side should be the cloudy. But in this case, dark is the sunlight. It's every hour of every day. These dashed lines are sunrise and sunset. So obviously there's no sun in the nighttime. But even in the daytime, there are a few cloudy days in June and July, as evidenced by this. There's just a lot of information that we can zoom into and zoom out and see trends. Small multiples are ways, if you don't have access to an animation, you want to add an extra dimension to your graph, you can repeat the same graphic multiple times. And that shows, instead of just 2 dimensions, this has a 3rd dimension to it. So this is the age of fish being caught out of northern European streams. And you can see right here, 1908, 1909, that same graphic. It's essentially the same graphic with data from different years, and you can see it shifting to the right, indicating that the fish that are being caught are older, and these streams are not being overfished. This is the same thing. This is a graphic of the age of your friends. These are when you're 15 years old, all your friends are between 15 and 29, basically. When you're 20 and you're in college, you're basically, all your friends live down the hall from you in your dorm, and that tends to be true. So right here, you've got friends, your own friends, plus you have your parents' friends. Right here, we have basically you have your own friends. All your friends are your own age because you're not living with your parents anymore. And then as you get older, then you start to get your friends and your kids' friends. And then you get really old, and your friends start to die off, and now suddenly you're 70 years old, and you just don't know that many 70-year-old people. So this is an example of seeing that trend over time. Every one of these things has the same x and y axis. They've just changed one variable on here. Here's another one. This is a lot of data here. This is from Consumer Reports. Consumer Reports rated a bunch of different make and models of automobiles, and that's what each one of these rectangle is. It's a different. This is the Chevy Malibu, and a Datsun something or other, Ford Granada, and each one of these is potential trouble spots. Each row is a potential trouble spot. So air conditioning and body exterior and body interior, so on. And then each one of these columns is the year. It's from 76 to 81. What they've done is these circles represent, if it's a white circle, unfilled circle, that means there's very few problems with that. So let me grab one of these things here. So the air conditioning on a 1978 Plymouth Volare was really good. It was really reliable. Hardly any problems with that. But on let's see, I'm having trouble reading this, but I think that's the body rust maybe, on the Plymouth Volare, the 1978 Plymouth Volare, 1979 Plymouth Volare, it's all filled in. So there's a lot of problems with that. And then, of course, partially filled ones are in between. The more dark they are, the more problems they had. So all this data here, we can look at it, we can just step back and say, oh, it looks like this car right over here, this Mercedes-Benz, well, that was a pretty reliable car. I mean, you probably paid more for that. That's why it's expensive. Whereas this car right here, this Plymouth Volare, was probably kind of a crappy car. It had a lot, maybe you'd buy it for cheaper, but you'd have a lot of repair bills on it. And this one right here is in between. This one seemed to have gotten worse over time, this Toyota Corolla. In the early days, it was good, but the last couple of models were not so good. Again, a lot of information that we can spot really quickly, and we can see differences between them because they're essentially the same graphic over and over again. And I have, actually, let me show you this. If my internet works, I brought this up here. This is, now that we have, again, not a tools talk, but there are tools that'll do this. This is immigration shown through animation. So if you're, they could have done this with small multiples. These are showing the paths that immigrants are taking. So the blue circles represent countries where there's a net increase in population. People are coming to those countries. And it looks like Australia and the United States, people are coming to those countries. And then this is areas like Syria, people are leaving those countries. The red represents people are leaving. There's a war in Syria, and so a lot of refugees are fleeing there. And you can actually see where they're coming from through the movement of these dots, is that people are leaving, it looks like Eastern Europe and going to Russia, for example. That's a common spot. Or they're leaving Western Europe and they're going to Canada. We could do something similar to that with multiples, just have multiple graphs, but with animation it's even more powerful. All right, let's see. Oh, good time for a quick review. A lot of truth, lie, context. Come on. Pauling, biochemistry, principles, vibrations, ducks. Density, high density, almost there. Oh, I want to talk a little bit about some of Edward Tufte's inventions, one of which became really, really popular. So if you use Sparklines at all, that's actually Edward Tufte's invention. Sparklines are great for financial data because we're able to stack them up really fast, so in a small space. The idea behind a sparkline is it shows the volatility of a trend over time, but it doesn't show every data point. So there's no x-axis, there's no y-axis. It just calls out significant points like the beginning, the ending, the high, and the low. And as a result of that, it's really compact, and you'll see in papers like the Wall Street Journal will list stock prices or commodity trading prices over time, and they'll be able to stack them all at once. You can see the trends upwards or downwards, and you can see the volatility of them and compare them really quickly. And in fact, in Excel, you can actually create a sparkline graph and stick it inside of a cell, which is really kind of cool. It's got an extremely high data density ratio, and so you can put a lot of sparklines on top of each other for comparison for small multiples. There's another graph I just mentioned just kind of for historical purposes, but I hardly ever see it in the wild. It's a slope graph, and Tufte invented this, and the idea is just to show some trends, the direction and magnitude of trends over time. So in this case, between 1970 and 1979, this is, I think, gross current receipts of governments during those two time periods. This one here, somebody sent me this one. I had never actually seen one in the wild. I mentioned that during a talk, and somebody sent me a picture of this one I thought was better. It's the consumer confidence of certain, I'm sure it's just from the US, but it's for during the decade between 2002 and 2011. During those 9 years, how did the consumer confidence, did it go up or down for all these public institutions? Like confidence in the police went down during that period. Confidence in church and religions went up. Some things went way down. Banks went way down. The confidence in the president went way down. The criminal justice system went up. So, it was just, I don't see this a lot in the wild, but I show it for historical purposes. The spark graphs, those are extremely popular. All right, more takeaways. So this is the takeaway of the whole thing. We're getting near the end here. I see some people taking pictures. I'll make these slides available later on. I'm happy to do so. All right, don't lie, children. Maintain graphical integrity. I know there's some people in the room that your boss is telling you to lie. So here's the data. Make it show this. And I'm not here to judge, but be aware that this can be a problem. That if you're doing it to deceive your users, it may have the opposite effect that you want. And if you're doing it to entertain your users, if you want to make it more snazzy because you don't respect your users, you don't think the data itself is interesting enough, maybe you need to get more data. Maybe you need to get better data to make the data itself more compelling rather than dressing it up with pretty pictures. But be aware of that lying is bad, okay? It can be self-defeating. Not just morally bad, but it can be self-defeating. Think about the data ink ratio. Like I said, this is the biggest effect it had on me as a software developer, is that iterative process. Maximize the data ink ratio. What's data, what's not data, and within reason, do that iterative process. If it's just decoration, just throw it out. There's no point to it at all. Don't worry about, I didn't say this earlier, but don't worry about if there's, some people say don't mix text and images together. Don't put too much text on your pictures. I totally disagree with that. I think it's just fine to put descriptive text to label your graphics as long as it adds to it. And I think it's perfectly okay to mix graphics in the middle of your paragraphs. I think that's fine too. Just do it intelligently. Do it in a way that's going to be clear to your users. Multifunctionality graphic elements, sometimes that's not possible, but it's kind of cool if you can do it. Just keep that data ink ratio high, and avoid legends. Avoid anything that makes it more complicated. If your users are moving their eyes back and forth, that's bad. And don't be afraid to have really dense data. It's more important that you structure your graphics clearly than it is that you remove all this extra stuff. We as human beings, we can see a lot of data. We can process a whole lot of data. Let's return to this. This is the graphic of Napoleon's march. Charles Menard was the guy that created it. He was a French engineer, and he could have just done whatever was the 19th century equivalent of next finish, if he wanted to. He was obviously a very good artist. He could have dressed it up and snazzed it up and made it pretty, but he didn't. These graphics here they don't tell the story in the way that Menard chose to tell the story. And that's what I want you to think about. As you're building your visualizations, no matter what tool you're using, start thinking about, after you hit next finish, take a step back and say, do I need all of this ink? Is some of it metadata? Can I get rid of this? Can I get rid of that? can I simplify this and increase my data inc ratio? And if I do so, the data will jump out more. I may even have room to put another series in there along the same axis, so I can start doing correlations. And once I start seeing correlations, then I can start coming up with hypotheses as to why those correlations exist. And this is information. This isn't just data. This is power. And your users will thank you. And my name is David Giard, and I am a technical evangelist for Microsoft, and I thank you. There's a party in about 9 minutes, so if you leave now, I won't. I'll totally understand. But if you want to ask me questions, I'm here.